There is something going on with light that most people never quite come to grips with, and I think it is because the way we explain it in schools is just a little bit wrong. Not wrong in the sense that it gives you bad answers, but wrong in the sense that it gives you a false picture of what is actually happening. And the false picture is comfortable. It fits with your everyday experience. But comfort in physics is almost always a warning sign that you have stopped asking the right questions. So let me ask you a question. When you flip on a light switch, you say the light travels from the bulb to your eye, and that sounds perfectly reasonable. You imagine a little photon, like a tiny bullet, fired from a glowing filament, zipping through the air, crossing the room, and landing in your eye. Clean, simple, satisfying. Now let me tell you why that picture, while not entirely useless, is hiding something absolutely astonishing from you. The first thing you have to understand is that asking how light travels is really asking what light is. And the answer to that question took the entire history of physics to sort out, and I would argue we still do not fully understand it in the way we would like. Newton thought light was particles, corpuscles he called them, little chunks of matter flying through space. Then came Young and Fresnel and Maxwell, and they showed beyond any reasonable doubt that light behaves like a wave. A wave in what exactly? That was the question nobody could answer satisfactorily. They invented something called the ether, an invisible medium that filled all of space because they could not imagine a wave without something doing the waving. And then along came Maxwell, who did not need the ether at all, not really. He wrote down 4 equations, and those equations said that electricity and magnetism are not 2 separate things, they are 2 faces of the same thing. And when you shake an electric field, it creates a changing magnetic field, and a changing magnetic field creates a changing electric field. And those 2 things feed each other and propagate through space all by themselves. No medium required. The wave is not a wave in anything. It is a wave of the field itself. Now that is already peculiar. What exactly is a field? A field is a thing we invented to describe the fact that space itself has a kind of condition at every point. At every location in space there is an electric field value and a magnetic field value. They are real in the sense that if you put a charge there, it will feel a force. Maxwell showed that these fields can ripple, and those ripples travel at a very specific speed, which he calculated from purely electrical measurements, and found it was 300 million meters per second. And that was the speed of light. So he realized right then that light is an electromagnetic wave, an oscillating electric field and an oscillating magnetic field, perpendicular to each other and to the direction of travel, passing through space and carrying energy. No bullet, no medium, just a self-sustaining oscillation in the fabric of the electromagnetic field. Now here's where it gets interesting, because when Einstein came along, he looked at Maxwell's equations and he noticed something that should have bothered everyone before him, but apparently did not bother them enough. Maxwell's equations say light travels at a fixed speed, 300 million meters per second, but fixed relative to what? In Newtonian physics, speeds add up. If I am on a train going 100 miles an hour and I throw a ball at 50 miles an hour in the direction the train is moving, someone standing on the platform sees the ball going 150 miles an hour. That is just common sense. So if light is going at 300 million meters per second relative to the ether, and I am moving toward the light source, I should measure light going a little faster than that. And if I am moving away, a little slower. But when people actually measured it, the speed of light was always the same. Every single time, regardless of how the observer was moving. That is not just strange, that is a crisis. It means the everyday rule about adding velocities is wrong, or rather, it is approximately right at low speeds, but fundamentally wrong at the level of principle. And Einstein took that experimental fact seriously and built the whole theory of special relativity around it. The speed of light is not just fast, it is a cosmic constant, a structural feature of space-time itself. But here is what I want you to notice. We have been talking about light traveling, and we have not yet asked the deepest question, which is, what is actually moving? Because when a water wave moves across a pond, the water itself does not travel with the wave. Each little bit of water just goes up and down in place. The wave is a pattern of motion, not a movement of stuff. So when an electromagnetic wave travels through space, what is moving? The fields are oscillating. Yes, but the field is not stuff in the way a billiard ball is stuff. The field is a property of space. So in some sense, nothing material is traveling at all. The pattern of disturbance in the field is what we call the wave, and that pattern propagates, meaning it recreates itself at each new location as time goes on. Now with photons, it gets even stranger. Because we discovered in the early 20th century that this wave can only exchange energy in discrete chunks, in quanta. When light delivers energy to an electron in your eye, it does it in one hit, not gradually. And the size of that hit is related to the frequency of the light by Planck's constant. So the energy is quantized, that is the photon. But the photon is not a tiny bullet following a definite path through space. That picture is wrong. I know it is the picture most people have, and I know it seems harmless, but if you take it seriously, it will lead you to say things that are not true. Here's what I mean. If you send a single photon at a double slit, 2 tiny holes in a barrier, and you put a detector screen behind the barrier, over time, 1 photon at a time, you build up an interference pattern. Bright and dark bands, just like a wave passing through both slits at once and interfering with itself. But each individual photon lands at one definite point on the screen. It arrives like a particle. It travels like a wave, and if you try to find out which slit it went through, the interference pattern disappears. The act of knowing the path destroys the wave behavior. How do you make sense of that? A bullet cannot go through both holes. A wave can. But a bullet lands at a point, and a wave does not, so the photon is somehow both and neither. And this is where I want to tell you about the way I think about this, the way that I find the most honest. It is a way of computing what light actually does, and it does not require you to commit to any particular picture of what light is. It is called the path integral, or in the context of light, the principle of least action as applied to quantum mechanics. Here is the idea. You want to know the probability that a photon will travel from point A to point B. The way you calculate that is, you consider every possible path the photon could take from A to B. Not just the straight line, not just the reasonable paths, every single conceivable path. Paths that curve, paths that go around the moon, paths that zigzag absurdly, every single one. Now for each path you assign a little rotating arrow, a kind of clock hand, whose angle depends on the total time the journey would take along that path. Then you add up all those tiny arrows, tip to tail. The final arrow you get at the end tells you the probability amplitude for the photon to arrive at B. And when most paths have arrows pointing in wildly different directions, they tend to cancel each other out. But when many paths have arrows pointing in roughly the same direction, they reinforce each other. And that region has a high probability. And it turns out that the paths near the straight line, the classical shortest path, all have arrows pointing in nearly the same direction, so they reinforce strongly. The crazy zigzag paths all have arrows pointing every which way, so they cancel. The result is that the photon is overwhelmingly likely to arrive as if it traveled in a straight line at the classical speed along the classical trajectory, but not because it was constrained to do so, because all the other possibilities canceled out. This is, to me, one of the most beautiful ideas in all of physics. The classical laws of optics, reflection, refraction, the straight line of light, all emerge from this quantum addition of possibilities. You do not need to assume that light knows the fastest path. You just add up the contributions from all paths, and nature does the rest. It is as if the photon sniffs out all of reality simultaneously, and then makes a choice consistent with that global smell. Now let me say something about what this means for the question of how light travels. In this picture, asking which path the photon took is not quite the right question. The photon does not take a path in the classical sense. The concept of a path presupposes a definite position at each moment of time, and quantum mechanics tells us that that is not how nature works at the most fundamental level. Position is something that gets determined at the moment of interaction, not something the photon carries with it throughout its journey. So the photon travels by exploring all paths simultaneously, and what we measure at the end is the result of that interference. But wait, you say, if the photon is exploring all paths, including crazy curved paths, does that not mean it is going faster than light sometimes and slower other times along those paths? And the answer is yes, in a sense. In the path integral, you include paths that would violate the classical speed of light. They contribute to the amplitude, but they contribute with rapidly varying phases, so they cancel almost completely. The net result is propagation at the speed of light. So even the rule that light travels at 300 million meters per second is not a fundamental constraint that the photon obeys at each moment. It is a statistical consequence of quantum interference. The classical picture emerges from the quantum reality, not the other way around. Now I want to talk about something that trips people up constantly, which is the relationship between the wave we describe and the photon we detect. When we talk about light as an electromagnetic wave, that is a classical description. It works beautifully when you have huge numbers of photons, and the quantum graininess averages out. Your radio receiver, your microwave oven, optical fibers, all those things are perfectly well described by Maxwell's classical wave equations. But when you are down at the level of individual interactions, when a single photon is knocking an electron out of a metal or being absorbed by a single atom in your retina, the wave picture has to give way to the quantum picture. And in the quantum picture, the thing that oscillates is not really the electric and magnetic field in the classical sense. It is the quantum field, which is a more abstract mathematical object. The quantum field is a field of operators, things that create and destroy photons, and its fluctuations represent the probability amplitudes for finding photons. And here is something that really makes people uncomfortable. The quantum vacuum, empty space with no photons in it, is not quiet. It is seething with fluctuations. Virtual photons, the books call them, though I want to be careful with that word because it suggests something that pops in and out of existence. And that is a colorful way of speaking that can be misleading. What it really means is that the quantum field, even in its lowest energy state, even in a vacuum, has an uncertainty in its value at each point, governed by the Heisenberg uncertainty principle. You cannot have both the field amplitude and its rate of change perfectly zero at the same time. So there are always these quantum fluctuations, and they have real physical consequences. They contribute to the Casimir effect, where two uncharged metal plates placed very close together actually attract each other because of the altered vacuum fluctuations between them. They contribute to the Lamb shift, a tiny but measurable change in the energy levels of hydrogen. These are not theoretical curiosities. They have been measured. The vacuum is not empty. It is a roiling, fluctuating ocean of field energy. So now I want to bring this all back to the title because I said light travels without moving, and that phrase is meant to shock you into questioning what you mean by traveling and what you mean by moving. If traveling means that some definite chunk of stuff moves from here to there like a billiard ball rolling across a table, then no, light does not travel in that sense. There is no definite stuff. There is an oscillating pattern in a quantum field. If moving means following a definite trajectory in space over time, then no, the photon does not move in that sense either. It has no definite position until it is detected. It has no single path that it followed. What it has is a probability amplitude distributed over all of space and time between emission and absorption. What does move, in the sense that we can precisely define, is the phase of the electromagnetic field, the pattern of oscillation, which propagates at the speed of light. And that is why the Feynman reality check is so important. Because the naive picture we have, the photon as a bullet, gets the answer right often enough that we never notice it is wrong. It predicts that light travels in straight lines, which is correct in the geometric optics limit. It predicts that light bounces off mirrors, which is correct on average. It predicts that light refracts when it enters glass, which is correct when you average over the correct quantum mechanical calculation. But it does not tell you why. And the why is buried in the interference of probability amplitudes, in the path integral, in the quantum nature of the electromagnetic field. And then there is one more layer I want to peel back, because even this picture, this beautiful quantum field theory picture, is not the end of the story, because we do not have a fully satisfying quantum theory of gravity, and gravity and the structure of space-time are intimately connected with the propagation of light. Light, according to general relativity, follows what are called null geodesics, the shortest paths through curved space-time. Light bends around massive objects, not because gravity pulls on it like it pulls on a baseball, but because the massive object curves the geometry of space-time itself, and light follows the straightest possible path in that curved geometry. So even the straight line that light seems to follow in empty space is only straight in the sense of the local geometry of space-time. Near a black hole or a neutron star, the geometry is so twisted that the straightest path curves back on itself. Light can orbit a black hole at a certain radius. The light is traveling in a straight line through curved space. Or you could equally well say space is bent and the light is just going straight. These are two different languages for the same physical reality. And here we have arrived at the deepest question, which is whether there is a fact of the matter about what light is doing when nobody is looking. I think the honest answer is that quantum mechanics does not really give us a picture of what is happening between observations. It gives us an extraordinarily precise and experimentally verified algorithm for predicting the outcomes of observations. The interpretation of that algorithm, the question of what is really going on in the world, is something that physicists and philosophers argue about and have been arguing about since the 1920s. I have my own views on it, as does everyone who thinks seriously about it, but I want to be clear that these are interpretive questions, not empirical ones. The experimental predictions of quantum mechanics are agreed upon. What they mean about the nature of reality is still open. What I can tell you is this: when you turn on a light and see the room flood with brightness, something remarkable is happening. Electric and magnetic fields generated by oscillating electrons in the filament are propagating outward, carrying energy, interacting with atoms in the air and in your retina, transferring energy in discrete quanta, each of which triggers a cascade of neural signals that your brain interprets as color and brightness and shape. Each step in that chain is described by equations of breathtaking precision. Quantum electrodynamics, the theory that accounts for all of this in detail, is the most accurately tested theory in the history of science. Its predictions agree with experiment to better than 10 parts per billion. And yet the picture it gives you of reality is one where particles do not have definite positions until they are measured, where probability amplitudes interfere like waves, where empty space is not empty, and where asking which path the photon took is not a question nature has a clean answer to. I find that thrilling, not uncomfortable. The universe does not owe you comfort, it owes you honesty. And if you are willing to look at it honestly, without deciding in advance what kind of answer you want, what you find is something far stranger and far more wonderful than a tiny bullet crossing a room. You find a quantum field, rippling with probability, exploring all of space, delivering its energy in discrete hits to the atoms in your eye. You find a universe where the classical world you see around you is not fundamental but emergent, built up from something irreducibly quantum mechanical underneath. You find that the light which has been flooding the world since the first stars ignited has never quite been what anyone thought it was, and that the process of finding out what it actually is has been one of the great adventures of the human mind. That is, I think, the most honest thing I can say about how light travels. It does not travel in the way you think it travels. Nothing about it is as simple as a bullet in flight. But the real picture, when you let yourself really look at it, is so much more interesting that I cannot imagine anyone being disappointed to learn the truth.